So, welcome everybody. It is a great pleasure to me to introduce Paul Schwahn from the University of Stuttgart. And today he'll speak about rigidity and stability of Einstein metrics on homogeneous spaces. Thank you, Paul, for accepting this invitation.
Yeah, thank you for inviting me to the seminar. So yeah, welcome everyone. Yeah, my topic was just announced. So first I'll explain a bit what I mean by when I speak about rigidity and stability of Einstein metrics. So let me introduce you to this. We start with some Riemannian manifold that has an Einstein metric. So means the Riemannian metric satisfies this equation. The Ricci curvature tensor is equal to some real constant times the metric. This means that G is an Einstein metric. And what we want to do is we want to consider the space or the collection of all possible Einstein metrics on M. In particular, we want to ask, are there any other Einstein metrics in this moduli space that are near G in some appropriate sense? Or even more, especially, are there any smooth curves of Einstein metrics that pass through G? Such curves are what we call Einstein deformations. So there are some obvious ways to deform an Einstein metric. For example, one can just multiply it by some scalar, some positive real number. It will still be a Riemannian metric. It will still be Einstein, but that's not really interesting. What we can also do is we can take a curve of diffeomorphisms and just pull back our original metric by these diffeomorphisms, and this will yield us a curve of Einstein metrics, because this equation here is diffeomorphism invariant. Yeah, so what we want to study are the interesting directions, so we somehow want to mod out these types of deformations. So in a sense, what we call essential Einstein deformations, the deformations that are transversal to those that I just mentioned. And what we consider is the reduced moduli space where we just, as I said, we mod out the action of R plus and the action of the diffeomorphisms. Now, we call an Einstein metric rigid if its equivalence class in this reduced moduli space is isolated. So that means there are no interesting ways to deform this Einstein metric. Yeah, the only way to deform it is by scaling or by action by diffeomorphism. So, and what Norihito Koiso showed in 1980 is that either G is rigid or it admits an essential Einstein deformations, inessential Einstein deformation. So, yeah, this means that the moduli space or the reduced moduli space is locally arcwise connected. All right, so we want to do some algebra. Algebra is always easier than analysis. So therefore, we linearize the problem. We consider it on an infinitesimal scale. So if we have such an essential Einstein deformation that passes through our original metric G, then we take the first order deformation, which just means that we differentiate this with respect to the parameter t at 0, and then our first order deformation H satisfies these three equations, which I will explain. So first of all, this operator here is the Lichtenowitz Laplacian. It's defined by a sum of, so this is nabla. This is what how I denote the Levi-Civita connection of the metric G. And if I take nabla star nabla, that's the rough Laplacian or Bochner Laplacian. Yeah, and this Q of R is some operator that depends solely on the curvature, on the Riemannian curvature of G. So the second condition here, this means that the trace of H with respect to G vanishes. the first order deformation, the tensor H is trace-free. That means we can think of it as transversal to scaling by functions. Originally, we only excluded scaling by constants. If we scale an Einstein metric with a non-constant function, then it ceases to be Einstein. So that makes sense here. Third condition means that the divergence vanishes. The divergence operator has a little index G because it also depends on G. It is defined in terms of the Levi-Civita connection. And this, in a sense, means that it's transversal to the action of diffeomorphisms. The first equation here is the linearization of the Einstein equation, of the Einstein condition, when you restrict it to these TT tensors, and TT tensors, TT stands for trace-free and transverse, meaning just trace-free and divergence-free. Yeah, and if we have a symmetric two-tensor H that satisfies these three conditions, then we call it an infinitesimal Einstein deformation, or short IED. And we denote the space of IEDs by this little epsilon of G here. Yeah, so.
Paul?
Yes.
The trace-free condition, I think that means only transversal to the usual scaling.
Transversal to the usual scaling would mean that the integral over the trace vanishes. But here I mean that the trace vanishes in every point.
Okay. Okay, thank you.
All right, so yeah, in essence, what we obtain is an eigenvalue problem for this operator. We want to check if this operator, if this Lichner-Robic Laplacian, has this 2e, which we call the critical eigenvalue in its spectrum on TT tensors. That's an important restriction here. Okay, so another point of view that makes this Lichner-Robic Laplacian interesting is the following. Consider for any Riemannian metric, we have the technical condition that the dimension of m should be greater than 2, sorry. This total scalar curvature functional, we just take the scalar curvature and integrate it. It's also called the Einstein-Hilbert action. And yeah, we have the characterization of Einstein metrics that G is an Einstein metric if and only if it is a critical point of this functional when it's restricted to the space of metrics of fixed volume. So this M1 here is how I denote, say, the space of Riemannian metrics with total volume 1. So this is crucial. Yeah, that we need this restriction here. Okay, so if we have such a critical point, we can ask how does the functional look like around this critical point? What is is it a maximum? Is it a saddle point, or what is it? So to do that, we consider the second variation. So this is some bilinear form, and we also have to suppose that the manifold is not isometric to the round sphere. That's just a technical condition. I'll explain that in a moment. We can split the formal tangent space of this space of metrics here. So bear with me. M1 is the space of metrics of fixed volume. And this tangent space is just the space of all symmetric two tensors that are given by first variations of curves that lie in this space. So we have the splitting, and this is orthogonal with respect to the second variation. Namely, the first component here is we have this little index G here. This just means that these are the set of smooth functions that are that have integral 0, because that comes from the restriction that we consider metrics of fixed volume. So we don't take all smooth functions. We have to mod out the constant ones. The second summand here is the space of all Lie derivatives of G. this is, in a sense, the tangent space of the diffeomorphism orbit. And the second here, this is what how I denote the space of TT tensors, so trace-free and divergence-free. So, and then we can analyze on each summand what this second variation does. So on the first summand, we know that it is always positive. So it means that G is a local minimum of S along directions of conformal change. Conformal change meaning that I scale the metric with some function or some non-constant function. We also know, since this is diffeomorphism invariant, that the second variation is 0 on the summand that comes from diffeomorphism action. So it's, yeah, it says it here. And on the third summand, we see that we get this Irreducible Laplacian again. So the second variation can be written like this on TT tensors. And we also get the critical eigenvalue 2e again. So this is another motivation, or another point of view that motivates us to study the spectrum of the Irreducible Laplacian on TT tensors. So, yeah, keep this in mind. What we know is that this second variation here on the space of TT tensors has finite co-index and nullity, meaning that there's the set of direction where this second variation is positive or 0 is finite dimensional. And this follows from the properties of this Irreducible Laplacian. Meaning that, keep in mind this space here is infinite dimensional. So along most TT directions, G is maximized. G is a local maximum of S, but not necessarily along all. The null directions are precisely the ones where this here vanishes, and this means that just H is an eigentensor to the Irreducible Laplacian to the eigenvalue 2e. So this is precisely an infinitesimal Einstein deformation of G. And what this motivates is that, the term stability, so we call an Einstein metric G strictly stable or strictly linearly stable if the Irreducible Laplacian is strictly greater than this critical eigenvalue on TT tensors. And we call it S stable. So this is not linearly, but this is in the global or in the local sense, but not in the infinitesimal sense. If G is a local maximum of S among the metrics of same volume and constant scalar curvature, we can notion it's linearly stable if we have a greater or equal than here instead of just greater than, and we call it linear unstable if this is not the case, meaning that there exists some symmetric, some TT tensor that is an eigentensor to the Irreducible Laplacian to a smaller eigenvalue than 2e. Note that if you can show that some metric is strictly stable, so this here holds, that means there are no eigentensors to the critical eigenvalue 2e. In particular, so it means that the space of ieds is trivial, and this means in particular that G is rigid, because if it has no infinitesimal deformations, it cannot have any deformations at all. All right, so conversely, we just went from Einstein deformations to infinitesimal Einstein deformations. Can we go back? So if we are given an infinitesimal Einstein deformations, can we find some essential Einstein deformation that has this as first variation? In other words, is H an integrable IED? And generally, this is not the case, but we can say when this is the case. We can characterize it. So what we do is we write down the Einstein equation by taking this Einstein operator here, operator from the space of metrics of volume 1 to symmetric 2 tensors, given by Ricci curvature tensor minus the total scalar curvature over n times G. metric G is Einstein if and only if E of G is 0. So then we linearize this. If we linearize this, okay, just that. If we linearize this, then we get this Rigidity minus 2e again. So this is, in fact, this is what leads us to the definition of ieds in the first place. This is just the linearization of the Einstein equation. And then we can ask, okay, we can linearize it, but what about higher order terms? So this is where the term integrable to order k comes into play here. So if we have some IED, we call it integrable to order k. If we find other symmetric two tensors such that we can build, or we can start building, some formal power series, and this satisfies that all the derivatives up to k of this gk inserted into the Einstein operator are 0. And what Koiso showed is also that if some IED is integrable into a curve, into an essential Einstein deformation, if and only if it is integrable to all orders. So meaning that there are no analytic problems. This problem is purely algebraic. So all we have to do, well, yeah, it's a bit of an understatement, but we have to check all these obstruction polynomials. So this here is a polynomial in H and H2 and so on. All right, so for example, take order 2. By definition, H is integrable to order 2 if there exists some H2 symmetric 2 tensor such that this here holds. This is the second order condition. And if we now, Koiso also studied the image of this operator here. So he showed that this is equivalent to just H. Okay, that's okay, sorry, that's that shouldn't be there. Ignore these two symbols. It's equivalent to the fact that this E prime of H is perpendicular to the space of infinitesimal Einstein deformations. So in particular, a necessary condition for integrability is that this here vanishes. We take this E double prime of HH, we take the L2 inner product with H. If this is perpendicular to epsilon of G, then this here should be 0, and we can explicitly write this out. Of course, we did this back in the days. And it's this, yeah, not exactly beautiful term, but it's workable. So, okay, yeah. So another thing in my topic is that I consider the problem of homogeneous spaces. And how do we approach this? So first, we have the following setting. We have some compact Lie group G, closed subgroup K. So we have just some homogeneous space M, G over K. G is compact, and we have it. It's equipped with some Riemannian metric that's G invariant. Okay. So now we use harmonic analysis to tackle this question. Remember, we want to study the spectrum of the Lichner-Robisch Laplacian. And spectrum of Laplacian, that's harmonic analysis. So in its full generality, we have the Peter-Weil theorem for homogeneous spaces. Looks a bit intimidating, but I'll explain it in a moment. If we have some homogeneous vector bundle, so say, for example, the tangent bundle or some tensor bundle that's associated to a complex representation, then we can take the sections in this bundle, and these can, so we have the left regular representation of G on the space of sections, and this decomposes into irreducible summands as follows. So this G hat is just the set of highest weights of irreducible representations of G. And so basically we run through all complex irreducible representations of G, and they all appear in this space of sections with some multiplicity, and the multiplicity is exactly determined by the dimension of this space. So this is the space of K invariant homomorphisms from V gamma to V, where V is the fiber of the bundle. So as an example, say we take the reductive complement. So okay, first say G is the Lie algebra of G, K is the Lie algebra of K. We take the orthogonal complement with respect to G or some other reductive complement, it doesn't matter. Then we can identify this with a tangent space of M at some base point. In fact, this is a representation of K, namely the isotropy representation. And if we now take, in effect, we want to study the spectrum on symmetric two tensors. So we take as bundle the bundle of symmetric two tensors, complexified, because we need complex representations for this to work. So the fiber of the bundle is the second symmetric power of our isotropy representation, complexified. And then if we apply the Peter-Weyl theorem, then we get this here. So each irreducible representation of G occurs here with a multiplicity given by this space. Okay, so how is this useful for us? How can we use this? Yeah, we want to study the spectrum of the Rigidity Laplacian, and since the metric G is invariant and the Rigidity Laplacian is defined in terms of G, it is a G invariant operator. So this means by Schur's lemma that on each irreducible summand, so we can imagine it as a sum like V gamma plus V gamma plus V gamma, and then V gamma prime plus V gamma prime, and so on. And on each of these irreducible summands, it acts as multiplication with a constant. So we have to keep in mind that these summands here occur with a multiplicity. So okay, and it's loosely right. It's not exactly right. What we the precise way of saying is that it acts for each gamma. So for each type of irreducible representation, we have some linear operator going from this finite dimensional vector space to this finite dimensional vector space. So it's actually not multiplication with a constant. That's a mistake here that I made when I wrote it up. It's multiplication with a matrix on this coefficient space. Yeah, this is what we call matrix coefficients, the elements of this space, and every such invariant operator takes a matrix coefficient to another matrix coefficient. This is what we call a prototypical differential operator. Okay, now the question is still, how do we actually compute the Lichner-Roberts Laplacian? Okay, so to do that, let me take you on a little excursus. Let me introduce. Let's just say we are on a reductive homogeneous space. So in particular, if G is compact, then this is reductive. We have some reductive complement M, and this reductive complement, or the choice of a horizontal distribution, induces a particular connection, which we denote with nabla bar, and this is called the Ambrose-Singer connection. So for each choice of reductive complement in a reductive homogeneous space, we get such a connection. And since G is a G invariant tensor, nabla bar of G is 0, so nabla bar is a metric connection. So these are all standard facts about reductive homogeneous spaces. But this connection has a torsion. The torsion is also an invariant tensor and can be given by this little expression here. So we take if we have two elements x and y of the reductive complement, then we take the Lie bracket of the both and project it down to the reductive complement again. Yeah, so Okay, I wanted to introduce the standard Laplacian. So suppose that G is a compact and semi-simple group. These two assertions are important because then we have a killing form that's negative definite. And if we just flip the killing form around, so we take minus the killing form, this induces a Riemannian metric on. So first, it induces it's an inner product on the Lie algebra G, and it's also invariant. So we can project, it induces by translation a Riemannian metric on the homogeneous space M, and this is what we call the standard metric of M. And now what we can do is we define the standard Laplacian with respect to this metric. So we take Barr-Nabla, the Ambrosinger connection, take its adjoint and match these together, get a type of rough Laplacian, and then add a curvature term completely analogous to the Lichner-Robisch Laplacian. Okay, what's the deal about the standard Laplacian? Well, the point is one can show that under these assumptions that this operator coincides with the Casimir operator of the left regular representation. And this is pretty nice because the Casimir operator is well understood. It's an operator that acts as multiplication by a constant, now for real, on each summand of type V gamma, and this constant only depends on gamma itself. And one can compute this constant according to this formula. So this is gamma, the highest weight. This delta G is the half sum of positive roots of the Lie algebra G. This formula is due to Freudenthal. Okay, so that's nice. But how does that help us? There are some nice simplifications when we assume that M is a symmetric space. Because then the torsion is, we have this formula for the torsion, but by the Cartan relations, if we take the Lie bracket of something that lies in M with something that lies in M, it lies in K. And if we project it down to M, we get 0. So simply by the Cartan relations of the symmetric space, this torsion vanishes. So now we have a connection that's metric and torsion-free. That's the Levi-Civita connection. So these two connections are the same, and hence these two Laplacians are the same. So the Lichner-Robisch Laplacian coincides with the Casimir operator on this left regular representation, and that's pretty nice. So we get the spectrum of the Lichner-Robisch Laplacian almost for free. We can compute it using the aforementioned formula. So does this answer the question of stability and infinitesimal deformability of symmetric spaces? Not exactly yet, because we forgot an important constraint. We forgot to consider the conditions of trace freeness and divergence freeness. So the condition that the tensor should be trace free is easy to accommodate. We simply observe that this always splits into a trace-free part, into a part proportional to the inner product. So we can simply consider the trace-free elements in this, and this behaves really well with this decomposition because it is just an algebraic property, and the metric is invariant, so everything is fine. But for the divergence, we have to think a bit more. How do we approach the divergence? First, we observe that the divergence operator, it goes from the space of symmetric two tensors, say trace-free symmetric two tensors, to the space of one forms, is also G invariant because it's defined in terms of G, the metric G, sorry. So if we have such an invariant differential operator, we can consider its prototypical differential operator on these matrix coefficient spaces. So we go to these, from these here to these occur in the decomposition of omega 1. So imagine we have omega 1 here instead, then we have this space on the right-hand side here instead. So, and now these are both finite dimensional vector spaces. We can compute them using representation theory, and we can compute the dimension in particular. So simply for dimensional reasons, this might vanish, or this might have some non-trivial kernel. So then we already know So say we have some gamma where we plug it into the Freudenthal formula and we get the critical eigenvalue. That means we have an eigenspace of the Lich-Nerobich Laplacian to the critical eigenvalue. And if the divergence happen to vanish on this eigenspace, this means we have infinitesimal Einstein deformations, which is cool. But this isn't the whole picture. So this is what Koiso did in the 1980s, and what he used to get his results on stability, infinitesimal deformability of symmetric spaces. But yeah, his list wasn't exhaustive. There were still some gaps, and these gaps have been filled recently. For that, we need an alternative way, alternative approach. For example, one can explicitly compute the divergence. So from the definition of the divergence and the properties of the Ambrosinger connection, we can infer this formula here. There should be a minus sign here, I'm sorry. Yeah, but that to compute this is we have to write explicit elements of the explicit matrix coefficients. We have to do all these computations. That's pretty tedious. It's possible, but it takes some time. Alternatively, one can also use some dimension formulas that are readily available now for any eigenvalue, for any potential eigenvalue to the Lich-Nerobich Laplacian. So yeah, it's a bit of a lengthy discussion to arrive at these formulas. It's not completely trivial, but it's possible. So yeah, we can get the dimension of these eigenspaces if we just consider the eigenspace on trace-free tensors, the eigenspace to the eigenvalue on one forms, and possibly we have to add the dimension of G. Okay, and this these two things are what has been used recently by myself, by Professor Semmelmann and Professor Weingart to complete the problem, to settle the stability and ID question for irreducible symmetric spaces of compact type. So now we have a list of all the irreducible symmetric spaces of compact type, and we can say this one has infinitesimal deformations, this one has not, this one is stable, this one isn't. I won't show the list here because it's not, I mean, yeah, there's not much to memorize in this, but I want to, okay, one aspect of the list I want to show, for example, this is the set, the collection of irreducible symmetric spaces of compact type that are infinitesimally deformable. So we have 4 families. We have the SUN, we have these 2 quotients of SUN, we have the complex Grassmannians, and we have the Cayley plane. And now the question is, I've asked it before, but you can ask it again, do these integrate into Einstein deformations? So are these integrable or are? And yeah, Koiso provided one example of a symmetric space. This is a product symmetric space, so not irreducible, that has infinitesimal Einstein deformations, but is rigid because these are not integrable. And recently there's been a paper by these authors, and they considered the infinitesimal Einstein deformations on SU2n plus 1 and showed that they are not integrable to second order. So this Einstein metric on the space is rigid. Unfortunately, for the even ones for SU2n, the obstruction to second order vanished, so one would have to look at the third order obstruction, which would involve even more work. Maybe someday. Okay, so we have talked about the symmetric case. Yes.
Paul, can you come back? Yeah, in this, do you know, what do you know about S stability? I mean, if these metrics are local max.
Ah, yes. Okay, so what we have is, okay, we can say pretty easily is that these S stability is implied by the strict stability and linear stability is implied by S stability. So it could potentially be the case that we have a space that's linearly stable but where G is, we can still ask if is G a local maximum of S or is it not a local maximum? And for that, we have to look at what the infinitesimal Einstein deformations do. And there has been an example of Zilla where, okay, let me get this right. I don't know what the space was, but it was a symmetric space where we knew that it was linearly stable, but not as stable because we have these null directions and they destabilized the metric to some higher order. So this is possible. We also have to look at the higher order terms in order to rule this out or to study this. So there are not many known results about S stability as far as I know.
So can you show again the symmetric spaces with deformations? So we don't know about any of these if one of these is a local max. Is not known.
Well, some of these are known to be unstable. So in this case, we already know that it's not a local maximum. Some of these are linearly stable, and I think which of those are? I don't recall exactly. I think SUN and E6 over F4 are among the ones that are linearly stable, and there we do not know, as far as I know, whether they are S stable.
Okay. Thank you.
Okay. So, okay, how do we approach the non-symmetric case? So in the non-symmetric case, we know that this Ambrose-Singer connection has torsion, so it does not coincide with the Levi-Civita connection, and consequently, these two Laplacians do not coincide. So what do? We can write the difference between these two connections explicitly. So we can write nabla equals bar nabla plus A, where this A is some invariant to one tensor, and we can write it at the base point like this. So it's proportional to the torsion of nabla bar. And if it's with this tensor A, we can write the Lichner-Robisch Laplacian in terms of the standard Laplacian. So we have these two different terms. This is a first order differential operator, and this is some constant terms. So in essence, recall this here is still the Casimir operator, and these are some pesky difference terms that we don't really know much about yet. Okay, so do we have any chance to compute these difference terms? For these, let me get to some examples where we have computed these. Example number one is when we are in the nearly parallel G2 case. So we have some 7-dimensional manifold, which is homogeneous, and it carries an invariant nearly parallel G2 structure, which manifests as some 3 form. So G2 structure means that sigma satisfies a certain positivity condition. In particular, sigma induces a compatible Riemannian metric on M. And the nearly parallel part simply means that sigma satisfies this differential equation here for some constant tau naught. Now, this G2 structure defines a canonical G2 connection, which we also denote with nabla bar, and this is no coincidence. I'll get to that in a moment. Okay, so this canonical G2 connection satisfies nabla bar sigma equals 0. So sigma is parallel by this connection, and the holonomy of this connection is G2. So why did I denote it with nabla bar? Because in this case, it actually is the same as the Ambrose-Singer connection. And furthermore, we can write the difference between the Levi-Civita connection and the Ambrose-Singer connection in terms of the G2 structure, namely it's tau naught over 12 times this 3 tensor here. which is pretty neat. And then we can do all sorts of algebra and do stuff. For example, we can pass under some equivalence to a bundle where working is easier. So this is a certain subbundle. This is a certain subspace of lambda 3 M. And then we get a comparison formula between the Lichner-Rovich Laplacian and the standard Laplacian. We can also translate the condition of divergence freeness to a differential condition here. So this simplifies it actually. And then we can do some more algebra and say somehow relate the eigenspaces of this operator to the eigenspace, or yeah, of this and this operator to the eigenspaces of the Lichner-Rovich Laplacian. For example, if we take the Bézier space, this is a homogeneous space defined by the quotient of SO5 by SO3, where SO3 is embedded via its irreducible 5-dimensional representation. Then we can show that we can get to the spectrum of this Lichner-Rovich Laplacian, at least to the small eigenvalues, and we can show that it does not admit any infinitesimal Einstein deformations, but it is linearly unstable. So meaning there are TT tensors on this space to a small eigenvalue of the Lichner-Rovich Laplacian. Okay, so
you can compute explicitly the minimum eigenvalue.
Yes, we can compute this. It's possible. So this passing to another bundle is just a little trick to make the computations easier. It's not generally needed. But yeah, the general strategy is to relate the eigenspaces of the Lichner-Rovich Laplacian to the eigenspaces or to subspaces of the eigenspaces of this standard Laplacian here. All right. Next example, it works really similarly. We have now we have strictly nearly Kähler manifolds in dimension 6, also homogeneous. This means just that, to remind you, the manifold carries an invariant almost complex structure. So this is almost complex. Then it becomes a Hermitian manifold if we assume that it has a compatible Riemann metric G, also invariant, of course. And the Levi-Civita derivative of J should be non-zero. So it's not a Kähler manifold, but it's nearly Kähler. It's strictly nearly Kähler because it's non-zero. And also this tensor here, this is a 2-1 tensor, should be totally skew-symmetric. And we have a list of these homogeneous, strictly nearly Kähler manifolds in dimension 6. There are exactly 4 possible spaces. First one is the 6th sphere with a round metric, which we can write as a quotient of G2 over SU3. The second one is a nearly Kähler S3 cross S3. Third one is nearly Kähler CP3. And the fourth one is a flag manifold SU3 over T2. And they all carry the standard metric. Okay. Yeah, so this almost complex structure induces a canonical Hermitian connection. That's what it's called, Nabla-Bar, such that the J is Nabla-Bar parallel and that the holonomy is SU3. So this is what we call an SU3 structure, essentially. And again, this Nabla-Bar coincides with the Ambrose-Singer connection. So that's why I called it Nabla-Bar. And we have this comparison formula between the Levi-Civita connection and the Ambrose-Singer connection. This is in terms of the complex structure, of the almost complex structure. And yeah, now we can do a similar spiel. So we can take this, the traceless tensors or the traceless, we can take this fiber here and take some equivalents so it gets easier to work with. It turns out it's equivalent to a sum of these two summands. And what we essentially obtain, I'm not going to write the exact result because it's a bit lengthy, but the message is that we take the eigenspace of the Lichner-Rovich Laplacian to some eigenvalue lambda on TT tensors, and we can write it as a direct sum of some eigenspaces of the standard Laplacian on this space, where we also have to carry the condition of divergence freeness again, so we get the kernel of delta here. But this is all, this can be computed. And these lambda I are not necessarily the same as lambda, but they depend on lambda in some explicit way. Okay, and using this technique, it's possible to show that all the spaces here, except S6, that's a standard sphere, that's stable, but all the other spaces are linearly unstable. We can also say how many unstable directions there are. And we also can say that only SU3 over T2 admits IEDs. Now the question is again, are these integrable? So I want to show in the last part of the talk, how do we actually check integrability in practice? So the strategy is we take the IEDs of SU3 over T2, we want to describe them explicitly enough in order to do the suitable computations with them. So we want to compute this second order obstruction. We take the E double prime of HH in a product with H. If you can show that this does not vanish, then we have shown that the space or that the metric is rigid. Okay, how do we describe the IEDs? So what we know at first is that the space of IEDs is equivalent to the Lie algebra of SU3. This is because the IEDs are given, so if I get back here, if we take the critical eigenvalue here, then we again have the sum of eigenspaces here. And the only one that does not vanish is the eigenspace to some eigenvalue, and this is given by, if we think back to the Peter-Weil decomposition, this is given by, okay, let me just scroll back here. This is given by the V gamma that's equal to the adjoint representation of SU3. So that's why the space of IEDs is equivalent to the adjoint representation, because this gives just the right eigenvalue of the Casimir operator. Okay. Now in the following, this is just a technical thing, but it's useful to consider M as a quotient of U3 by T3. Note that U3 is not semi-simple, so we cannot take the standard metric here, but we can extend the inner product in a way that's suitable. Okay, now we take an element of SU3 and we want to describe some IED by it. So what we do is we let the adjoint representation of U3 act on Xi. This gives us some function on G, some smooth function on G. And now we can, with values in SU3, and now we can, I mean, SU3 is the set of 3 times 3 matrices that are, trace-free and skew Hermitian. So we can write it like this, where these are some functions, some smooth functions on G. Okay. Then we can take, also according to this matrix stuff, we can take a basis of the reductive complement. I'm not going to write the details out, but basically what we get is we combine all this to get a function on G with values in the symmetric power of M, also trace-free. That's K invariant. So K was T3. So if we have a function on G with values in some K representation, that's K invariant. This means that this function projects to a tensor on M. So what we get is a symmetric 2 tensor, a trace-free symmetric 2 tensor on M. And in fact, this is an IED. Okay, now we have described these IEDs, and then we want to compute its derivatives. So recall that the Leibniz-Civita connection is equal to the Ambros-Singer connection plus some difference term. And because the Ambros-Singer connection is well adapted to the homogeneous structure, it just corresponds to the directional derivative on the space of functions. So we can just use the commutator relations of U3 to get at the components of nabla bar H. Also, we can write down this A here as a 3 tensor explicitly. So I'm doing a bit of abuse of notation. Here, A is an endomorphism on tensors of possibly any rank. And here, A is a 3 tensor that's given by the difference of the two connections. Yeah, but algebraically, it works the same as extending a connection on the tangent space to a connection on arbitrary tensors. Okay, so we can write this out explicitly, also using the basis EI, and then we just combine this with H, and we get the components of AH. Okay, if we combine this all, we can do a little integration by parts here. So we can put this nabla to the others, to some other H, and this as well. So we only have to compute one covariant derivative. And then what we get in a sense is some polynomial in these functions. Okay, so we have this polynomial, and we want to know, there's a parenthesis, shouldn't be there. We want to know whether this integral vanishes over this polynomial. So yeah, it's a polynomial in those functions. Those functions are essentially we can view them as one forms on SU3, or on elements in the dual space of SU3. So we can view this thing here as a homogeneous cubic polynomial in Xi, so the element of SU3 that we chose to begin with, or the element that parametrizes all our IEDs. And now if we integrate this over the Lie group G, this just simply amounts to projecting it to its G invariant part, because everything that's not G invariant will simply integrate to 0. So we would go from the third symmetric power of SU3 to the space of G invariant elements in this. So now we can ask, okay, how do we project this to its G invariant part? And it turns out this space here is one-dimensional. It's generated by a simple polynomial, namely just I times the determinant of SU3 matrices. And then we simply have to check, okay, we take this I, we take the inner product with the determinant, and we see if we write this in a similar fashion, then we can straightforwardly compute that this is not 0. So what we've shown is that no IED on this space is integrable, and hence the Einstein metric on this space is rigid. I think that was the last part. Oh no, it was not the last part. Okay, this is what I've done so far, but now to an outlook on how we can tackle the problem on more general homogeneous spaces, and not only on these particular examples. So recall these identities. We have the difference of the Leibniz-Civita connection and the Ambros-Singer connection. We can write it like this. We can write the difference of the two Laplacians like this. And now the question is, how do we compute the spectrum of the Lichner-Rovisch Laplacian? So for this symmetric case, the strategy was simple. This is the same as this, and this is the Casimir operator. So we simply check the spectrum of the Casimir operator for suitable eigenvalues, namely the critical eigenvalue 2e if we want to check for IEDs, or some subcritical eigenvalue if we want to check for unstable directions. And then we have to look at whether the divergence vanishes on these eigenspaces or not. For non-symmetric spaces, it's not quite that simple. So the strategy is to compute the Lichner-Rovisch Laplacian on sufficiently many eigenspaces of this Casimir operator, and then check the divergence again. But what does sufficiently many eigenspaces mean? I mean, how many eigenspaces do we have to check? So up to which eigenvalue of the Casimir operator do we have to go to rule out small eigenvalues of the ignorable Laplacian. So meaning it would be useful to have an estimate of the difference between these two operators. And I've done some preliminary computations. So there are, we can write the difference as depending on this A tensor and also on this Ambrose-Sanger connection here. So we can estimate this roughly by some combination of Casimir operators. And yeah, note that here we have a peculiar site, namely an operator norm of a nabla operator. So usually these kind of operators are unbounded, but here we restrict it to a summand of type V gamma. So it's a representation where we know that this it's a finite dimensional vector space. So we know how we can estimate this by the rough Laplacian. And this gives us this estimate here that depends on the Casimir operator on V gamma. All right. So the hope is that these methods will be of use to compute this Lichner-Roberts spectrum on homogeneous spaces where we do not have any additional structure. Okay, and now this is really the end of my talk. Yeah, thanks for your attention, and I'm open to questions now.
Thank you, Paul, for the nice talk. Is there any question for Paul?
Paul,
yes,
I have a question.
Sure.
Concerning these other terms in this last page, if you have an eigentensor of the Lichner-Robic Laplacian, these other terms acts diagonally, acts by a scalar on this eigentensor?
Well, that's the problem. We cannot expect them to be diagonal. So okay, let's get back to this prototypical differential operator here. Where was it? Here. So yeah, on each of those, so V gamma is always associated to an eigenspace. It's an eigenspace of the Casimir operator. So it corresponds to eigenspaces of this standard Laplacian. And so we have this operator here going from this space of coefficients to this space of coefficients, and it can in principle do anything there. So yeah, the eigenspaces would
okay,
split,
but take an eigentensor of this, or an eigenvector of this finite dimensional map, and I wish to know the other operators, how they act, the other operators on this, because the Casimir operator acts by
the Casimir operator is just a
by
constant,
scalar
right?
in the whole space, right?
Yeah, exactly. That's just a constant depending on gamma. Yeah. For the difference terms, it's the same. They will also give us some operator on this space, and it can in principle look like anything. So we do not a priori know much about it.
Okay, and could you go again to the last slide? And about the strategy in the standard non-symmetric case.
Yes.
You compute sufficiently many eigenspaces, and
yes.
And what do you do with these numbers? I'm not sure if I understood the method.
Yes. Yeah, the point is that, okay, we have some estimate between those. So say we know that Okay, recall we want to look for small eigenvalues that are less or equal to 2e of this Lichner-Robisch Laplacian.
Yeah.
So the intuition is that these should also correspond to small eigenvalues or eigentensors to small eigenvalues of this standard Laplacian here. But these eigenvalues are not the same because there are different terms. But these different terms are bounded by bounded by some constants, bounded depending on gamma. And we would expect that there is I mean, if we would not have such bounds, then we could say expect if we have an eigenspace of this here to the eigenvalue 100, it could still be that the Lichner-Robisch Laplacian could be like, could we have a small eigenvalue on this space? So we would have to go through a lot of irreducible representations. I mean, in the symmetric case, where we looked for small eigenvalues of this Lichner-Robisch Laplacian, one would like consider one or two or at most three different irreducible representations, compute their Casimir eigenvalue, and then know that above it gets larger, so these are not of interest. But the question is, how far do we have to go here? How many irreducible representations do we have to run through to be sure that we won't find any small Lichner-Robisch eigenvalues anymore? That's what I mean by sufficiently many.
Okay, but you pick one irreducible representation with eigenvalue, with Casimir eigenvalue less than 2e. And
no, not necessarily less than 2e.
Okay,
it would depend on the bound
small
that we get. Yeah.
Okay, small, and you check the divergence of the corresponding
we do
tensors.
that. We do that in the last step. So first we compute that if we actually have some interesting Lichner-Robisch Laplacian eigenvalues, and then we can ask, okay, we have an eigentensor to the Lichner-Robisch Laplacian to a small eigenvalue, and then is this eigentensor divergence free?
Okay. Very nice talk. Thank you very much.
Thank you too.
Is there any other question for Paul or comment? Well, if that's not the case, so we can thank again Paul. Thank you again.
All right.